Okay, this is test 3, lesson 4. In this lesson, we're going to actually start solving equations, both exponential equations and logarithmic equations, using some of the properties that we've already covered. Our first line of defense, we're going to talk about exponential equations first, is if we can somehow manipulate the exponential equation such that the bases are the same, like you see right here. If we can get to where the bases are the same, notice that in this setup, if the bases are the same, the only way this equation can be true is if the exponents are the same. And so we can simply go from this equation here, just set the exponents equal to each other, and then solve the variable. So keep in mind that the problem that we're encountering with these is that our variable is in the exponent. That's what makes it an exponential equation in the first place. So this is a little cluttered, but follow along with me here. Let's start with this equation. Here we have 5 raised to the 3x minus 6 equals 125. So our variable x is in the exponent. So the first step that we could do is, boy, if we could turn that 125 into a base of 5. Now we won't always be able to do that, but if we can, it will make life simpler. So 125 happens to be a power of 5. It happens to be 5 to the third power. So 125 is the same as 5 to the third power. Now notice our bases are the same. So we can simply set the exponents equal to each other. 3x minus 6 equals 3. And then add 6 to both sides and divide by 3. So our solution is 3. All right, so you can see how simple the problem becomes if you can get the bases to be the same. Notice over here in this equation, however, we have the bases are 8 and 4. Now 8 and 4 are not connected exponentially. However, they are both powers of 2. Right? We can't change 8 to some power of 4, but we can change them both to powers of 2. 8 is 2 to the third, and 4 is 2 squared. And then recall that in this scenario here, when you have a base raised to an exponent raised again, you simply multiply the exponents. That's what's happening right here. And then the same thing on the other side. So we can just set the exponents equal to each other. And so we'll have x plus 2 right here equals 2 times x minus 3. Distribute rid of the parentheses. Now you have 3x plus 6 equals 2x minus 6. What are we doing here? You see I subtracted 2x from both sides. That's why it's just x here. And then I subtracted the 6, and that's what made it negative 12. And that's our solution. All right, so if we can get the bases to be the same, then that's the easy way to solve an exponential equation. However, what if we cannot get the bases to be the same? If that's the case, then we're going to have to use logarithms. So the steps here are to isolate the exponential expression. Before you start throwing logarithms in there, you want to get the exponential expression completely by itself. Add, subtract, multiply, divide, do whatever you have to do to get the exponential expression by itself. Then we can take the logarithm of both sides of the equation. That's just that universal property of algebra. As long as you do the same thing to both sides of an equation, the equality will still hold. Then once we take the log of both sides, then we can use one of these 3 properties here. If the base is not e or 10, then we could use either natural log or common log. In this case, we'll use the natural log and use the power rule that we learned in the last lesson, that x can move out front. So notice the exponent x just moves out into the front of the expression. And remember, our goal here is to get x down out of the exponent so that we can deal with it. Natural log of b is just going to be some number, and we'll just treat it like a number in the rest of the equation. If the base of the exponential happens to be an e, then using the natural log, we can just simply cancel it out. The natural log and the e cancel each other out, and it just leaves an x. Similarly, if the base is 10, then we can use the common log, and they'll cancel out and just leave us an x. All right, so let's see this in action. So right here, I have 5 to the x equals 134. We can try all day long. We're not going to be able to convert 134 into a base of 5. There's 5 raised to, there's not a whole number that you can raise 5 to get 134. So we'll simply take the natural log of both sides. That's what we've done there. Then we'll use the power rule to move the x out front of the natural log of 5. And so we have x natural log of 5 equals natural log of 134. Well, here is just where we need to cling to the fact that the natural log of 5 is just a number. This is exactly the same type of algebraic equation if we had 3x equals 9, right? I've got some number multiplied times x, so I just divide by that number. Same thing here, I've got some number multiplied by x, so let's just divide by the natural log of 5. That's why it moves down there. So this right here is our exact answer, the natural log of 134 divided by the natural log of 5. If we need a approximation, we can put that into the calculator and get 3.04. So that's how we use logarithms to solve exponential equations. Here's another example. I've got base 10 raised to the x equals 8,000. Since this is base 10, it would be in my best interest to use the common log on both sides, because the common log and the base 10 will cancel each other out, and I've just got x. That's what I'm looking for. So the answer to this is just the log of 8,000. I can put that into the calculator if I need to and get x equals 3.9. Let's see, even if it gets a little complicated here, follow along with me. I've got two numbers here. I've got two exponential expressions. I've got one on the left and one on the right. So I can't really isolate one of those, or I've got them both isolated, however you want to think about it. So we'll go ahead and take the natural log of both sides, just like this. We'll move the exponents out front. The exponents will move out front. And then I really just need to remember that natural log of 3 is a number. So let's distribute the number. So the natural log of 3 times 2x is here. Natural log of 3 times -1 is here. Natural log of 7 times x is here. And the natural log of 1 is right here. So notice now I have 4 different terms. 2 of them, this one and this one, have an x in them. So let's get them on the same side of the equation. Let's get the ones without the x on the right side. Now that I have these two expressions on the left that have an x, I can factor out the x. And that'll leave 2 natural log of 3 minus the natural log of 7. All of this mess here in the parentheses is just a number, right? We could jam all that into the calculator and get a decimal approximation if we wanted to. But for right now, we're just trying to solve for x, so we're going to divide both sides by everything that's in the parentheses. And that's why it just ends up down here in the denominator. That is our answer. That's the exact answer. The natural log of 3 plus the natural log of 7 divided by 2 natural log 3 minus natural log of 7. Again, put all that into the calculator if we need to and find an exact, or an approximation, 12.11. All right, so that's how to use logarithms to solve exponential equations. This one I just wanted to show, this is an example of, we've kind of glossed over that first important step with solving exponential equations, and that is get the exponential expression by itself. On all the examples so far, it's been by itself already. So we want to isolate this e to the 2x. All right, so first I need to add 5 to both sides, and then I need to divide by 7. So that's where the e to the 2x equals 9 comes from, just because I added 5 to both sides, and then I divided by 7. So now that I'm here, I can take the natural log of both sides. The natural log and the e cancel out, and that just leaves me the 2x, and then I'm left with natural log of 9 on the right, which is just a number. Dividing both sides by 2 gives me my exact answer of the natural log of 9 over 2. If they want a decimal approximation, put that into the calculator. All All right, so this is just an example of, remember that first step is to isolate the exponential expression. All right, now we're going to shift gears. Now we're going to solve logarithmic equations. We're going to kind of cheat here because what we're going to do, first of all, isolate the logarithmic expression, and then we're going to convert it to exponential form. Just like we first learned when we learned about logarithms, how to go from exponential form to logarithmic form, we're going to do that, convert it to exponential form, and then solve it like we just learned how to solve exponential equations. All right, so on solving logarithmic equations, we convert it to an exponential equation and solve it that way. Notice step 4 is in red. This is crucial. I told you there were 2 times in this class where you had to check your proposed solutions. The first one we learned at the very beginning, that was the radical equations. Anytime you have a radical equation and you solve for x, you have to check the answer and make sure it works. Same thing here with logarithms. This is the second time. If it's a logarithmic equation, once you find your answer, you have to check it because you could get an answer doing all the correct mathematical steps, but it may be not valid. Okay, and the only way to know is to check it, to plug it back in. All right, so for instance, notice right here, I've got this logarithmic equation, right? So my first step then is, well, isolate the logarithm. And so it is, the logarithmic equation or the expression is isolated. Convert it to exponential form. So the base is a 2, so that's where the 2 comes from. The logarithm is an exponent, so that's why the exponent has to be the 3, and then it equals whatever's on the inside. So notice once we've done that, it makes the equation pretty trivial. 2 to the third equals 8, add 4 to both sides, and you end up getting x equals 12. However, because it's a logarithmic equation, I have to make sure that works. So I plug 12 in for x and make sure I get a valid solution. Honestly, on these, if this is going to blow up, it's going to be right here. The problem you would run into sometimes if you plug in a number into the logarithm, if it's not in the domain. Right? So if you get a log of 0 or a log of a negative number, that means that answer is not valid. All right. Now, keep in mind, I didn't say if x is negative, then you have to toss it out. That's not true. Just let me give you a separate example here. What if you had a problem that was log is x plus 4, or log of x plus 4 equals something, and we found a solution for x happened to be -3. Well, just because x equals -3 does not mean that x is not valid just because it's negative. Because if I put -3 right here in for x, that would just be the log of +1, and that's fine. So it's not the fact that x is negative, it's the fact that when you plug it in, it makes whatever's inside the logarithm negative. That's what makes it an invalid solution. What else do we have here? Okay, so on this one, again, just a reminder that you want to get the logarithmic expression by itself first. So we're going to divide both sides by 4 here. Right, that's where the 8 turns into a 2. Now we've got the log by itself, so we can convert it to exponential form. Natural log is a base of e. The log is the exponent, so that's why the exponent's 2, equals 3x. So divide both sides by 3, and that gives me x equals e squared over 3. Remember, e squared is, or e is just a number. So this is the exact answer right here, e squared over 3. We could put that in the calculator and get 2.46. Now, on this one, whenever you're checking, I highly recommend you use the exact answer. It'll just cancel everything out cleaner, right? If you put the 2.46 in there, you might get an exact equality at the end. You'll get 8 equals 7.99999, because if you do the decimal approximation, you're going to introduce a little bit of error. But if you put in the exact answer, notice here the 3's cancel right off the bat. That makes it e squared. Then the natural log of e squared, the natural log and the e cancel out, and 4 times 2 is indeed 8. Let's see. This is sometimes where those properties we just learned will come in handy. I've got 2 logarithms, right? But I can't convert it to exponential form if I have two logarithms. So I'll use in this case, the product property, because they're being added together, to combine it into one logarithm. The log of x plus the log of x minus 3 is the log of x times x minus 3. Now I have a single logarithm on the left. I can convert it to an exponential equation. So this is the common log, right? There's no base there, so the base understood to be 10. The exponent, the logarithm equals the exponent, that's a 1, and that equals x times x minus 3. So the good news is it's no longer a logarithmic problem. However, it is a quadratic, because when you distribute this x, you're getting x squared minus 3x. Subtract 10 from both sides, because we always have to have a quadratic equation equal to 0. And then this one will actually factor into x minus 5 and x plus 2. So that means x equals 5 or x equals negative 2 are our proposed solutions. All right, it's either positive 5 or negative 2. Now, don't toss this one, the x equals negative 2, just because it's negative, right? That doesn't make it invalid. What makes it invalid is if we plug it in and it makes a negative or 0 inside of a logarithm. So let's check that out first. So we found our two solutions, proposed solutions, 5 and negative 2. If I put a 5 in here for the x, notice I get the log of 5 and the log of 2. So right here at this step, I'm pretty confident this is going to work, because it did not cause me to be outside the domain of the logarithm. The log of 5 times 2, so I can combine these two, and it turns out to be the log of 10 equals 1, which is a true statement. So 5 checks out. We're okay with the 5. Negative 2, however, right off the bat, when you put in negative 2 in for x, then you end up with a domain violation, a domain error, because you cannot take the log of a negative. So that's why we have to discard the negative 2. The only possible answer is positive 5. The only valid answer. Okay, one last thing with logarithms, what sometimes works out is this is similar like we started with of trying to make the base the same with an exponential equation. Well, here, if we have more than one logarithm, but we can kind of manipulate it to where it's going to be a log equals a log. Well, because of the one-to-one property, the only way for this to be true is for the insides to equal each other, as long as it's the logarithm of the same base, right? So this has to be, whatever this number is right here, the b has to be the same thing there. So if I have two logarithms of the same base set equal to each other, I can just drop the logarithms. It looks like we're canceling out the logarithms. That makes mathematicians cringe when we say it like that. That's not really what's happening. Really, we're using the one-to-one property to set the insides equal to each other. Okay. Then you solve for the variable. Okay, and it's still a logarithmic equation, so be sure and check your proposed solutions. Let's see an example here. All right, so I've got the natural log of x minus 3 on the left, and I have two natural logs on the right. So the first thing I'm going to have to do is combine these two into a single logarithm. Because it's subtraction, I've got to use the quotient rule. That's why it's 7x minus 23 on the top and x plus 1 on the bottom. Then I've got the natural log of something equals the natural log of something else. So I can just simply set the insides equal to each other. So that's why the natural logs went away. So now I have this equation. Yeah, it's a little messy. We'll clean it up, but it's no longer a logarithmic equation. So first step here is to multiply both sides by the denominator. So I've got x plus 1 multiplied on both sides. The reason that was to cancel it out on the right. So now I don't have any denominators anymore. I have to multiply these two together to get this expression. FOIL, distributive property, box method, whatever you want to do. Now it's a quadratic, so I've got to get everything on one side. So I'm going to subtract 7x and add 23. So that's where I get this expression, x squared minus 9x plus 20 equals 0. This will factor into x minus 5 and x minus 4, which means either x equals 5 or x equals 4. Those are my two proposed solutions, right? It's still a logarithm. So we have to check them. If we put a 5 in here for x, there's the x, I put in a 5, there's the x, we put in a 5, there's an x, we put in a 5. And simplify this, it turns out nothing blows up. I always have a positive integer inside of a logarithm, and I end up with a true statement. So 5 is okay. Let's try it again with a 4. So there's an x, I put in a 4. Oops, missed it. There's an x, I put in a 4. There's an x, I put in a 4. So again, looks like nothing blows up. I always have a positive integer inside the logarithm, and I end up with a true statement. So 4 works as well. Therefore, both of the answers are okay. That can sometimes happen. All the examples before, one of them ended up being invalid. One of the answers did, one of the proposed solutions. But in this case, they both work. So you could have 2 good answers. You could have only 1 answer. You could have no answers. There are some logarithmic problems that don't have a solution. So watch out for those as well. All right, this concludes test 3, lesson 4, where we learn to solve exponential and logarithmic equations.